Okay, so here we go. This is the 2001 mechanics, number 2. All right, so it says an explorer plans a mission to place a satellite into a circular orbit around the planet Jupiter, which has a mass of 1.90 times 10 to the 27th kilograms, and a radius of 7.14 times 10 to the 7th meters. A, if the radius of the planned orbit is r, then use Newton's laws to show each of the following. And then it has you deriving those two equations that we did just a minute ago in the previous one, right? So do I need to go through A? We just did it, so I'm not going to, even if you want me to. All right? So, because we just did it. All right, everybody good?
Yep.
All right, part B. The explorer wants the satellite's orbit to be synchronized with Jupiter's rotation. This requires an equatorial orbit whose period equals Jupiter's rotation period of 3.55 times 10 to the 4th seconds. Determine the required orbital radius. So first of all, do you guys understand what's going on there? Remember, your period depends on your radius. All right? Like Earth satellites, like if you were watching TV last night. Sorry, my brain just stopped there. If you're watching, I don't know, whatever. What is the name of TV station? CNN, thank you. Wow, my brain just totally shut down. So when you watch CNN, they have what's called a geosynchronous satellite. Is that right? Geosynchronous? Yeah, and so it orbits the Earth at the same rate that the Earth turns, so it takes 24 hours to go around. There's one radius that will make it do that. That was the worst explanation I've ever done. So anyway, we're trying to find our radius. So long story short, if it's not too late, a minute ago we came up with this. We know what the period is. We got to find the radius, right? What mass am I going to use? What planet are we orbiting? Jupiter, right? So you want Jupiter's mass, right? Follow? All right, so if you do that, the answer you get is not on this piece of paper. 2001, 2001, there we go. So you get 1.59 times 10 to the 8th meters. Good? All right. Finally, part C. This is the one that I wanted to make sure we understood because I feel like I did a rotten job explaining this in the video. All right, C says, suppose the injection of the satellite into orbit is less than perfect. For an injection velocity that differs from the desired value in each of the following ways, sketch the resulting orbit on the figure. J is the center of Jupiter, the dashed circle is the desired orbit, and P is the injection point. So that just means where it enters into orbit. Also describe the resulting orbit qualitatively but specifically. So here's the deal. So just a minute ago, you found that equation for V circular, right? And you found that V circ was the square root of GM over R, right? Okay? So the idea is you've got this satellite. So here's the center of Jupiter. Here's the orbit I'm trying to achieve. Okay? That is meant to be a perfect circle. Follow? All right, so I'm trying to get it into orbit at that point in a circle. Okay? But the problem is my velocity is slightly off from the circular velocity that we intended. All right, so in part 1, it says when the satellite is at the desired altitude over the equator, in other words, at point P, its velocity vector has the correct direction, but the speed is slightly too fast. All right, so what that means then, you guys, is this. Means that I haven't given myself enough room. All right, so if it's going too fast, what's going to happen is your orbit, it still orbits it, but the path is elliptical instead of circular. Okay? So the idea is because you're launching it a little bit too fast, it's sort of able to get farther away from Jupiter. Okay? And so the path you get would look like this. Okay? So it only touches at this one point. Okay? So the circular orbit is entirely within this shape I just drew. What's the name of that shape? An ellipse. All right? Now remember, Kepler's first law tells us that if your orbit is elliptical, then the object being orbited, in this case Jupiter, must be where? At one of the focal points, right? So this is one of the focal points of my ellipse. And then there's another focal point over here. What's at that focal point? Nothing, just empty space. Okay? Make sense? All right. So that's what happens if you launch it a little too fast. You get a slightly elliptical orbit. There you go. All right, now, what if we, I think Roman numeral 2 says, what if we launch it slightly too slow, correct? So you get kind of the same result. You still get an elliptical orbit, but this time, it stays within the circle. So now your ellipse will look like this. So here's Jupiter, one of my focal points, and now my other focal point is up here. Okay? So the idea is now, instead of going farther away and then coming back, here it falls in towards Jupiter and slingshots around it. Good? Questions? All right. Yeah.
Yeah, never mind. Sorry.
Now, this assumes, notice, remember, what did this dot here represent? Jupiter, but more specifically, the center of Jupiter, right? Okay? So we're not given any reference here about the scale. It's possible, maybe this is the planet Jupiter. Okay? So it's possible that if it's going slow enough, it could crash into Jupiter if that elliptical path carries it, you know, through the surface of Jupiter, through onto, I guess. Make sense? You know what I mean. All right, problems, you guys? I'm getting lots and lots of blank stares. Are we okay? All right. Any questions on those two FRQs? Okay, cool. What else do you guys want to look at from the